For the next part, we're actually going to take a step back to the maps, and technically, we are going to revisit the implementation of a map, and we are looking at the cases where we have a simpler requirement that instead of having to keep it in a sorted order, that maybe if we just know how to find elements maybe that's good enough. And so going back to the notion of maps, so we have this key value pairing, right? So we have key value pairing. So you have key to value, given a key, find a value. And if this is all that we care to do, then we don't actually need a structure like a binary search tree. Now, the nice thing about binary search tree is that you have this sorted ordering of the keys. And that is useful if you want to be able to move from one key to keys that are nearby in terms of the value. I mean, the content of the key. But if we are just going to do direct point-to-point put and get in terms of the map, then we don't need that particular sorted ordering. So in that case, we can relax the requirement, and in some sense, we can get a benefit of being able to do the put and get in a faster way. So this map, we are going to care now only for the following operations, which are the put and get, right? So get is to fetch, to put is to introduce a new value. Now, for the purpose of this discussion, we are going to assume we have unique keys. So we have unique keys. The keys are unique. So why is that important? It is important in the case that if you get the key, then you expect that you only get one value. If you put something and you put an identical key to something that existed before, then you expect that the previous key, the previous value is going to be overwritten. So the behavior of the put is that we are going to replace a value, and we're going to return the previous value that we put in, right? Okay, so these are the main operations of the map. Now you have the remove as well, in which case what you do is that you don't just get it, but you basically also remove it at the same time. All right, so now let's say we want to do this, right? So and previously we looked at some examples of the operations of the map, and the idea here is that the map is going to keep track of the key value pairing. So you put in 5 and A. 5 is the key, A is the value. Then you're going to have that inside the map. You put 7B, so then it's going to maintain it in some way, right? Now, this is an abstraction. How exactly you are keeping this inside the map depends on your implementation strategy with respect to the structure that you use to store all these values that allow you to do this key value pairing. Okay, now we are going to look at a simple example first, which is what we call an array-based implementation. And later on, we're going to see how can we improve on this, right? Okay, so the first implementation of it, we're going to call it Unsorted Table. Okay, that's not a very elegant name, right? But I think the idea here is just that you keep it as a regular list. And you're going to kind of just pile it up, right? Every time you introduce a new key value pair, just add it into the list. And along the way, you're going to, when you need to fetch, like get a key, then you just need to be searching for that element within your list. So one of the key ideas is that there is a list, right? And every time I have a key, one of the basic operations we need to do is what we call find index. Basically, what it does is that we're going to do a linear search. So we are going to do a linear search within this array to find where exactly the key should be. Because it is unsorted, so we are not storing it in any particular organized way. And therefore, we are going to basically just do a brute force, look at every possible place, and as soon as we get that particular key that we want, then we can return, right? Which means that in the best case, this can return us the value in O1. So in the best case, right? Now, in the worst case, well, in the worst case, the key that we want to put in is actually something new. So we haven't seen it before, but in order to be sure of that, we need to be searching across every possible location and all the way to the end. And then we are going to essentially go through everything. So there's going to be ON. Then you have the average case. Now, the average case requires us to have a certain assumption about the way that the elements are distributed, right? So meaning that if we are going to do searches, where are we going to find it? Well, if it's completely random, then we don't quite know. Sometimes we find it in the first place, sometimes we find it in the second place, third place, all the way to the nth place. And if we assume that that particular probability is uniform across, so in that case, we can kind of average it out, right? So meaning that it could be the first place, it could be the second place, it could be the third place, all the way until the nth place. And then we're going to average it out by dividing it by the n possibilities. Now, if that is the case, right, the top n here, 1 to n, the summation, so then you get an n times n plus 1 over 2, right? And then you divide by n again, right? So if you divide by n again, then the two n's, the n on top and the n below, they're going to cancel out. So which means that on average, you expect this to take n plus 1 over 2. So more or less half of it. But n plus 1 over 2 is still on, right? So which means that this particular behavior is going to get us on in the average case. Okay. Now, this is the notion of just keeping things in a list, and we're going to search it whenever we need to. Okay. Now, so the get and the put then will both require this particular operation of linear search, which we call find index. We need to find it when we get, right? Definitely, because we are fetching. But even when we put a value, we still need to do the find index first. The reason is because of the assumption of uniqueness. So the key has to be unique. So before I put in something new, I need to make sure that it didn't exist before. Because if it existed before, then what I will need to do is that I will need to replace it instead. So I need to search first. And in the worst case, I have to go all the way to the end of the list to find what I'm looking for. Okay. All right, so in that case, that kind of explains why it is that any sort of operations on this unsorted list implementation of a map is going to be ON. And that is given essentially by the linear search that we need to do pretty much in all of them, right? So either we want to get, put, or remove. In all cases, we need to first locate that particular key that we are going to manipulate. Okay, so that is kind of inefficient, and we can do better than that. And the principle that that we see as to what is responsible for this complexity is the search, right? So the problem is a search. So we get ON because we have to search. So the best way to deal with it is that we avoid the search. So now if you want to avoid the search, then we would have to store it someplace where we can identify very quickly. So instead of looking at different places, we're just going to look at one place. I mean, ideally, we only look at one place. Now, think of it like the way they organize the library, right? So you have all these books, right? And there are like thousands or even hundreds of thousands of books, and they have a problem. Like, how do you organize all these books? Well, you're going to organize all these books depending on how people are going to search for them. And so the librarians have developed certain schemes to do so. And one of the schemes of organization is called, they call it Dewey decimal system, right? Based on the content of the book, the topic, they're going to categorize it into a particular number. So then that number is like a 3-digit code that tells us about, is it about economics, is it about geography, is it about politics? And then they're going to group all the books that share this same code on the same shelf. So if you're looking at finance books, you're going to be looking at, a collection of books that are in the same shelf. Now, you're not going to go through, you're going to go directly at a particular shelf. And the reason why you can do that is that because given a book, you can actually identify what the address will be. without having to search through the whole library. So the way to do that then is that we have to associate the address of an element with its content. That means that all you need to do is just to tell me what the key is, and then I can process that key such that I can identify immediately what the address should be for this key. And that can be done in what is called hashing. So if we take a look at what is the meaning of hashing, well, hashing essentially is a function. It's a one-way function. This is what hashing is. What does it mean I have a one-way function? It means that I gave you the key, give me the address. Now, you don't have to be able to go the other way around. Like you don't have to go from the address and then give me the key, right? I mean, that is not necessary in this particular case, because our purpose simply is just to locate where a particular key is going to be when we want to store that inside our data structure. Okay. Now, the simplest implementation of this is that, since the key has to give us the address, why not just make the key itself the address? So then we don't even have to do a lot of processing, right? So if I'm assuming that the key itself is an integer, then I can just pretend that I'm going to have a space for every possible key. So I'm just going to create some big array. And if the key is 1, then I'm going to put it in 1. The key is 3, I'm going to put it in 3. The key is 6, I'm going to put it in 6, right? 7, then I'm going to put it in 7, right? Now, if I do it in this way, then we have a very simple hashing function. In fact, it's so very efficient because you can always get to what you're looking for in one step. All you need to do is just to find that address. Now, the only problem is that there is a restriction, and that restriction is that your key cannot be more than your array size. Well, that is one restriction, or you can think of the same restriction in a different way. You have to create a big enough array that will match the maximum of your keys. And that could well be a very, very big array. Now, it's not, okay, the bigness of the array itself is a problem, but it's not the only problem. The other problem that you have is all the spaces that you are wasting. Because then when you declare an array, and you need an array in this case, right? Because you need to do direct addressing based on the index. When you create an array, you basically allocate this space at the beginning. So you're going to say, okay, I'm going to create an array, and I want an array of this size, which means that the operating system is going to allocate that much space. But if in the end you're not using most of them, then it will be wasted, right? So for that reason, usually we try to minimize the use of the array structure itself. It's not that we can avoid it. If you want to do direct addressing, we still need an array, but we can at least make it smaller. Now, the problem with making it smaller is that we can no longer guarantee an exclusive slot for every element. So which means that then we need to evolve into a slightly more complicated structure, where in this case, we are asking some keys to share. So some keys to share. Now, the benefit that we get is that then this extent of the array can be saved, right? I don't need such a big one. In exchange for that, I need to create these buckets. But these buckets can be a dynamic data structure, which means that I don't have to pre-allocate the spaces. For example, I can choose a linked list. And if I do use a linked list, I don't have to declare anything. I would just need to add stuff in as and when I need them, right? So that means that then I get a trade-off between the array size, which has to be pre-allocated at the beginning, versus the dynamic size that I can create as I go, right? So that means that, you know, it's a trade-off between how much down payment you want to make versus how much cost pay per use that you get, right? So which means now we are going to shorten this array size. In exchange, we are going to tolerate that some of these keys are going to share the same space. So they go to the same bucket, and now there is a cost of searching the secondary storage, which in this case is the bucket. So which means that if I index 25, 3, and 14 all to the same array index, right, is going to point to a bucket, and then I have to go through the elements in the bucket to really find which one I'm really looking for. Okay, so then the remaining problem then is that, well, since it's no longer one-to-one, so which means that I need to have a function that is going to take me from the keys to what is going to be the index. So that is going to be what we call the hash functions. Now, before that, okay, so let's take a slight diversion to the way that the machine or the specific programming language are going to store all these numbers. Okay, so in the case of Java, we're going to care about integer. And the reason is because in Java, all the objects has the particular method called Hashcode. And this Hashcode can return an integer value. Okay. To decide where it's going to be allocated in terms of a hash table. So this requires us to return an integer. So which means that whatever object it is, I mean, it could be a string, you still need to return an integer. It could be a floating point number, you still need to return an integer. It could be some complicated, like a big object, like you know, it could be like a something like a car with a plate number, with a machine, engine, and so on. As long as it's an object, in the end, you can organize them. So you need to write a hash code that is going to combine all these things, right? Okay, so now what is an integer in Java? Well, integer in Java is represented as the 32-bit number. Okay, so here there is a technical term, sign two's complement. I think you have covered this in 106. Did you? You did, right? So like different ways you can use binary representation of an integer. And 32-bit simply means that you have 32 spaces, and each space can be occupied by a 0 or a 1, right? So that means that technically, if you use all of them as to encode a number, so then the biggest number that you can do is going to be 2 times 2 times 2 times 2, right? All the way, because there are 32, it should be 2 to the power 32. Now, but this is if you don't care about the sign. So there is a sign, it's positive or negative. So if you care about the sign, then you want to preserve one of them, 1 bit, to tell us a sign. Is it positive or is it negative? That's a 1-bit information. So in that case, I can't go to 232, right? So in this case, then we can go to, and I still have 0 too, right? So which means that instead I can go to 2 to the 31 minus 1. So that's the largest positive value I can get. The smallest negative number I can get is going to be minus 2 to the 31. Okay, so that is the largest and the smallest number. Now, what is 2's complement? Okay, so to get a negative number, we just need to invert all the bits and then add 1. So which means that we get a 2. So what is a 2 in binary? 2 in binary is just 1 0. So just 1 0, but of course it's 32-bit, so you pad it with all zeros. So you get 32, well, you get 30 zeros followed by 1 and 0. So this is 2. So what is negative 2? Well, negative 2, you're just going to invert all the bits. So it's going to be 1 1, right? So all the way up to here, and then invert this to 0, invert this to 1. So you get 1 1 1 1 1 1 0 1, and then plus 1. If you plus 1, then the 0 1 is going to convert to 1 0. So then this is going to be 32-bit representation of minus 2. Okay. All right. So okay. Hopefully soon it will be clear why we need to know this stuff. Okay. Now, so the key that we presume to be an integer. So meaning that we need to find a way to convert anything and everything to be an integer. What we have shown before is that any 32-bit number is an integer. So that means that as long as you can write out a bit, it is an integer. It's going to be some value within the range of the integer. So which means that although your original key is not an integer, you can always convert it to integer, as long as you can derive a 32-bit representation of that particular key. So meaning things like, okay, integer is 32-bit, right? Short is 16-bit. So then you can always make it longer, right? If you have a short representation, you can make it longer. Just pad it, right? Okay, sometimes you can have a different one. For example, in the floating point number, it's a little bit different, right? So I think you also learn how to represent them in terms of this. So you have to preserve some for the non-decimals, and then you've got some other part that encodes the decimals. But in that case, there is an implementation in Java that will allow you to just map it into integer bits. So you can also get this 32-bit number. Now, what if it's longer than 32-bit? You get 64, right? Well, if you get 64, like long or double, so these are 64 bits, well, we're going to presume that 64 is a concatenation of two 32. So which means that assume that your key, instead of having a single key of 32-bit, you have two keys that are 32-bit each, and then you find a way to combine the two keys into one key. Yeah. Yeah.
Why do we invert everything else beyond the first bit?
Say that again.
Why do we invert everything else beyond the first bit for the two in binary? First one is just the bigger number of number to the left and right give you the number. So it's 1, 2, 3, 2, 4, 8, after the negative.
So your question is on this one or on this one?
On the bottom one.
The bottom one, yeah. So what about it?
So my understanding of the negative thing, right, is just the first number becomes 1, and then the rest remains the same, like the magnitude, right, remains the same.
Oh, I see what you mean. Okay, so you have a different encoding scheme. You're saying.
If this is the correct way of my understanding.
Okay, so the 2's complement is a specific representation. And there are different types of representations of the bit representation of integers. I am just quoting this because this is the actual one that has been used by Java. This is the actual one that has been used by Java. So in case you actually do your own experiment, you realize this is what they do. So it means that you can take an integer -2, and if you ask Java to produce its binary code, then you're going to get this one. And the reason why is because they use a specific scheme that is called signed 2's complement. It's not the only scheme. There are other schemes. Okay.
So in another scheme, it could be just 1 and then the same.
Maybe, yeah. Okay. Right. Okay. So it was okay. So I was at the key, and the key can be complicated. And we say that if you have longer than 32-bit, 64, then you just presume they are a combination of keys. Now, one example of that, right, you can even just go beyond 64 bits, because, for instance, you can have a string. And if you do have a string, then you can break it down into components. On each component is going to be a character. Each component is going to be a character. And this particular character actually has an integer value. So every character value, every character object within this in Java is associated with some number. And that particular integer value is going to be some code in some encoding scheme for the character. Okay, like ASCII, Unicode, and things like that. Now, so in that case, essentially when you want to get a key, your key is going to be a tuple of several integers. It's not one integer, it's several of them. And when we have such cases, then we need to have a way to combine them into one integer. Okay, now, how do we do that? So, okay, so we're going to look at this in terms of, we're going to break it down. We're going to decompose this into 2 steps. So the objective at the beginning is that we are going to start from the key, and then in the end, we want to know the specific address to store it within some array structure. So now, if we understand where the key is going to be, let's say, right? Now, we have 2 methods here. So the first method is called a hashcode, and you can park this method with the object. So think of it as you have some object, and this object is going to have a hashcode function. So let the object decide what its hashcode is going to be, right? Because they are the ones who actually understand how to encode similarity between different elements. Now, but the output of this is going to be an integer, which means that the integer part of it is going to go from minus 2 to the 31 to 2 to the 1 minus 1, right? So that range is very big. And so then we need to employ another function that is called a compression function. And this compression function is going to take this big range and squeeze it down to some smaller range, right? Which if our array is size n, then it's going to be from 0 to n minus 1. Now, this compression function is going to be parked with a hash table structure, because the hash table is the one that knows what is the size of the array. So basically now we are going to split the responsibility of developing a hash function into these two partitions. The original object has to decide how do we compute its hash code. The hash table has to decide what is going to be the size of the array that we need to implement that. So in that case, then, just think of it in that way. That means for you to actually design a hash table, you have to do it in two places. One place is the hash table itself, where you're going to control how the sizing is going to be. Do you need to resize, when you resize, and how you resize? And we are going to leave it to each individual object to code the hash code. The hash code, two objects that are the same should get you the same hash code. And therefore, how do we tell when two objects are the same? Well, that is up to the people who implement the object itself, right? So then you go to the object and do this hash code, okay? All right, so we're going to talk about each one of them. We are first going to talk about the hash code, okay? Now, what gives us this hash code? We're going to talk about several schemes. And the basic idea of this different ways to do the hash code essentially is to get us to know how to combine several components of a key into a single integer, because each component itself is integer. So we're always dealing with integers as far as we are concerned. But we want to find a way to combine them, aggregate them into a single integer. Now, one way to do so is by, again, coming back to the bit representation. And if we start at the bits, right, we can just manipulate the bits in some way, and therefore coming up with a way to represent this. Now, in the end, all we need to do is just to represent things in terms of 32-bit. And as far as we have 32-bit, we always have an integer. Okay, now this is just an example, right? You can have other types of logical operations. We're going to use the Xor operation here. Now, in the case of Xor, you are only one if exclusively one of the two bits are 1. So if A is 0, B is 1, so that is 1. A is 1, B is 0, that is 1. Otherwise, you get 0 and 0, right? So that's exclusive OR. Now, how do we use it? Well, let's take the same string, right, ABC. So these are 3 integers, and we want to convert them into a single integer. Okay, how do we convert it into a single integer? Well, we take A and we take B, and we transform A and B to be binaries, right? And these are the binaries. Of course, they are 32-bit, but we're not going to worry about the prefix, which are all zeros. So if we take these two, and then we take the XOR, then we just need to go this bit by bit. And if the bits are the same, it's going to be 0. If the bits are different, it's going to be 1s. So let's say if I take the first 2 binary strings, right? They are only 1s in the last 2 positions, because it's 0 and 1 is 0. The rest of them is going to be zeros, right? Now, I take that, and I can do another XOR with the third one, right? So in this case, 1 and 0, this gives me a 1. 1 and 0, a 1. 0, 0, 0, 0, 0, 0, right? The rest are zeros. So in that case, then, okay, is that too many zeros? Okay. So now, then we end up with a final binary string that is 1, 1, 0, 0, 0, 0, 0. Okay. Now, any 32-bit representation is an integer. So it turns out that the integer value is 96. All right, so this is just the code that gives us the thing, right? We have the following, the caret sign. Basically, it's an XOR operation. So you get this caret sign. and then you do that. And well, it's already an integer, which is h, so you don't actually need to do anything. But here, because we want to visualize what the binary string is, then you can convert it to a binary string, and you get this one. Okay. Now, this is kind of neat, right? So because any operation involving 32-bit will always give me 32-bit. So I don't go out of bounds. You know, I can always keep it within the scope of 32-bit. But there is a problem, right? And it depends on whether or not it is a problem to you or not, right? Because in this case, the ABC, if this is a set, if you read it as a set, that you have a set of 3 characters, A, B, and C. So then what you want is that whether it comes in any permutation, A, B, C, B, A, C, C, A, B, C, B, A, and so on, you want them to have the same hash code. Because if you read it as a set, then 2 sets that have the same set of elements, although they come in different sequences, should still be the same. Now, if that is the case, then you want to use something like this, which is going to give you the same hash code, even though the 2 strings come in different sequences. So you have A, B, C, B, A, C. Now, if to you this doesn't matter, in fact, you don't want this to matter. Let's say, for example, you're comparing 2 groups of things, and you see them as sets. So whether it is cats and dogs, or dogs and cats, and you consider them to be the same set, then you want to specifically go after a hash code that will not make distinction between the sequence in which you see those elements. But in the case that you actually care about the sequence, to you ABC and BAC are 2 different things, then this is a bad hash code. It's a bad hash code because it gives 2 things that are different the same hash code. So which means that technically we are going to create some duplications in terms of where the hash code is going to be stored, right? So because of that, then there are other types of hash functions that you can use to solve the problem. Now, another hash function you can use is polynomial function. So polynomial is by definition like a sequence, right? Because it's basically a sequence of something like this, right? So you have a square, well, the a is here, right? Times x plus x1, for example, right? x0, okay? A times x1 plus 0, let's say, times x plus x2, right? So let's say this is a polynomial function. It's a polynomial in terms of the a. So that means you can read all these x's as essentially being the coefficients to that polynomial function. Okay. Now let's take a look at an example, right? So we had the same thing as before, which is the strings, right? And it turns out that the strings that we have now is A, B, C. Now, as we have seen before, A, B, and C, they each code for a specific value, whether it's 97, 98, or 99. So if I want to encode ABC, well, firstly, I'm going to pick a constant, okay? The A here, by the way, is not the same as the A here, huh? The A here is the constant to the hash function. And let's assume that constant is 27, okay? We're going to talk about why 27, all right, later. So and the 27 here, and if my string is at ABC, so what I want to do is that I'm going to compute 27 squared times A plus 27 times B plus 27, right? So this gives 27 to the 0, which is C, right? Now, of course, if I have D, then my string is going to go longer. So then I'm going to have 27 cube of A, 27 square of B, 27 of C plus D, right? So there's another polynomial. And if my sequence is even longer, then, you know, I just keep incrementing this. Now, it turns out that there is a more efficient way in which you can compute this. Because in this case, you can compute it, you can formulate this in a different way. So that is executed by this algorithm. So maybe this is a little bit easier to see, right? So how do I compute this function? Well, firstly, I'm going to set the hash value. This is basically the whole hash value, right? To be 0, right? And then I'm going to have a coefficient 27. So the first time I go inside this loop, initially my h is 0. And then I'm going to add the first element, which is A. So which means that my first H, right, let's call it H1, right, is going to be A. Okay. Then I'm going to come into this again. And my second H, right, which is H2, right? So what I'm going to do is that I'm going to multiply my previous H, H1, with 27. So I'm going to get 27A. And I'm going to add the next one, which is B, right? So that means that now I'm going to have this 27A plus B. Now, the third time I go inside here, then I'm going to H3. So I'm going to multiply everything here with 27. So I get 27 squared A plus 27B. Then I just add another C, right? So now if my sequence goes longer, then I just need to execute the loop one more time. Then I'll get 27 cube A, 27 square B, 27B, plus whatever else is coming at the end of it. So which means that we can pretty much do this in a single pass. So we don't have to be computing each of these separately. We can compute them together. We can increment this power at the same time as we are processing the different elements to that sequence. Now, if we do it in this way, then we are going to produce some integer value at the end of it. And since we start out with low numbers like 97, 98, and so on, in the end, we get something like 70,000 something. But the good thing here is that ABC and BAC are now going to give us two different hash codes. So they're no longer the same. So we are now encoding the sequence. So that essentially is the essence of it. When you think about how to design a hash code, you basically think about what is an important information within this. How do I know that I can differentiate between two different keys? And I would like to be able to incorporate only the information that is actually important in distinguishing between two keys. If the sequence is not important, you should use something that doesn't care about the sequence. If the sequence is important, then you should use something that has a sequence within the hashcode function. Okay. All right, so we're going to talk about one more thing, and then after that, we are probably going to take a break, okay? Okay, so the next hash code is called Cyclic Shift. So we're going to operate again on the bit strings. We're going to operate on bit strings. Now, let's say if you take a 5-bit cyclic shift, right? What it means is that you take a 32-bit value, and then you're going to shift it by 5 bits to the left. Then it's going to flow over, right? It's going to overflow to the left, which means that the 5 bits that are on the leftmost has to cycle forward, right, to the end. So which means that the red part here, that is now the prefix in the original bit string, is going to be now the suffix in the post shifting of the value. Now in Java, this is accomplished through this code, right? This is a 3-step thing. Okay, the first step is a left shift. So here H and then double arrows, right? 5 to the left. What it means is that you take the original binary string, you shift it by 5 bits to the left. And as you shift, what happens is that there's going to be padding. The paddings are going to be zeros. Okay. Now, then you take the same bit string as before, and you shift it to the right by 27. So then it goes to the right. Now, why is it 3 signs, right? It's 3 because it's unsigned. Unsigned means that regardless of whether or not it's positive or negative, we always pad with zeros. If you use 2, then they will take into account the sign. So whether you're going to pad by 1 or pad by 0. All right, so now in this case, you push it by 27, then you're going to push 27 zeros in, and then just, you know, basically have this one, right? Now, you can think of each of these basically like a filter. So this is a filter that essentially takes the original string, and then it tries to differentiate between the 2 parts. So the parts that are to the left and the parts that are to the right. The first operation is basically taking the parts that are to the right. And we would like to capture that part, right? The one that, the second one, that is a right shift, is trying to capture this left part. And so then at the end, what we need to do then is just to take an OR. And within this OR, so any 2 zeros, right, is going to be 0, right? Anything that involves a 1 will be a 1. And eventually, you're always taking an OR against a 0. because the zeros are the padding. So then in effect, what you're doing is that you get a cyclic shift. Okay, you get a cyclic shift by taking the original one, okay, and then trying to split them by trying to identify what is the rightmost 27, what is the leftmost 5. And at the same time as you're doing that, you're also shifting. And in the end, the OR is just going to combine them into a single string again. Okay, so this is basically what this code is doing. Now, in the same way here, it's going to always result in 32-bit value. And so it's going to encode some integer. And in this case, ABC, BAC is going to be sensitive to the sequence in which you are doing you're processing the keys, or the elements of the keys. Okay. After here, any questions? Yes.
When do we use cyclic shift?
So what do you mean by when do you use cyclic shift?
Cyclic shift, like you say polynomials because of sequence when order matters. When we use cyclic.
The same. So this is also the case. Cyclic shift basically is just to transform one integer to another. So you want to transform one integer to another in a predictable way. So in the case that, well, you basically have, in the polynomial case, you have to identify what is this coefficient. In the cyclic shift, you basically have a different way to identify, to basically randomize the distribution of it. So two of them are possibilities. In effect, it's not just a matter of which function you use, but also which parameter you use to solve this. Now, this is actually discussed in the next slide, right? Now, this is actually decided by experiments, because at the end of the day, the intention is to minimize what we call collision. Collision is when you have two keys mapping to the same index. And when you have two keys that have the same hash code, we call it they are colliding, which means that they're likely to go to the same bucket. And as much as possible, we want to avoid that. So now this is a specific experiment that is done on 230K English words. Now, if you do it on some other language, your outcome may be different. But in this case, they were looking at the shift, like how many bits you shift by, and what is going to be the implication with respect to the number of collisions that you get in the total or in the maximum. Now, maximum means like how many words would actually finally have the same hash code. It can go as much as 623 if you never shift, which means that if you don't shift, there is enough repetitions or the patterns within the data set, then in the end, we are going to have many words mapping to the same one. All right. Now, it turns out that even a shift of 1 or 2 already reduces by a lot. By the time you get to a shift of 5, you get to 3. In fact, the lowest shift is around 2, right? But at the same time, you also want to see how many collisions you have. Because every time you have a collision, then you have to store them in the same place, right? So the reason why they use an example of 5 is because it minimizes the number of collisions. So in the same way, if you want to use the polynomial function, then you would have to search for what is the correct coefficient. Now, there are probably some default values that people use to solve these things, right? But if you want to optimize for it, then you would have to have some form of anticipation of what your data distribution is like. Then you can better optimize what your hash function is going to be. Okay. So before we move on, the hash code again, right? In case some of you are still unclear about certain parts of it, we'll discuss the hash code functions again before we go on to the next part of the hashing concept. All right, so the idea of the hash code is that you have the key, and from the key you want to go to an integer, right? So that is the idea. So from key to integer. Now your key itself might actually be composed of one or more integers. So the idea here is that there are several integers here, and so you need to have a way to combine them in a particular way such that you produce an integer hash code, and to do so in a way that encodes the notion of similarity. So meaning that two keys that are the same, you want this to be having the same hash code, so that every time you put it in and you get it out, you're gonna come to the same address. But if two keys are different or similar but not the same, then you want them to have different hash codes. And the reason is because you want to be able to distinguish between things so that they don't collide, right? A collision is when two different keys map to the same hash code. So we look at 3 different ways to do this, and there are more than 3. We're just getting a sample of them, and one of them is called an XOR, exclusive OR, in which case you take the collection of integers that are in your key. So we're going to read this as characters, but characters are just integers in this case. And so if we are going to do this at the level of bits, so we have the bit string representation. So 97 in binary is going to come up to this. So if you want to visualize it in Java, you just need to call on this method, integer to binary string. Then it's going to essentially output the binary string to any integer. Now, so you have these different components that are each binary, and you want to combine them into a single integer. So then we're going to use XOR in this case. So we're going to take a loop, and within this loop, we start off with 0. And then we're going to take that and XOR that with any one key, right? A 1 at a time. So in this case, we're going to take an XOR with A and B and then C, right? So in this case, let's first try with the first 2. So if we take the XOR, it means we're going to do bit by bit. So the first bit, 1 and 1, so that is a 0, right? Because according to the table, 1 and 1 is a 0. 1 and 1, the second one is another 0. In fact, they are all zeros, right? Except the last 2 bit is a 0 and 1. So 0 and 1 is a 1, and then 1 A XOR B, then you get this, right? Which is 0, 0, 0, 0, 0, 1, 1. Then if you keep going, you take another XOR, and you're going to XOR this with C. And C here is 1, 1, 0, 0, 0, 0, 1, 1. So, okay, let's focus on those, right? So 1 and 0, you take the XOR is a 1. So this is a 1, this is a 1. Now the rest are 0, 0, 0, 0. They're all zeros. 1, 1 is also a 0, right? 1, 1 is also a 0. So in the end, you get the following hash code, right? Which is the same as this one. 1, 1, 0, 0, 0, 0, 0. And this is binary. And this is the integer, right? So this is the integer of the same binary. Okay, so that's one way to do it, and we say that the XOR, it has this commutative property, which means that you do it in any sequence, it doesn't change the outcome. So you can do A XOR B or B XOR A, and so on, and because of that, it encodes for the set type of property, where you have these different keys, and as long as you have the same set of keys, it doesn't matter it comes in which sequence, you still get in the end the same hash code. Okay, so that's why for ABC, for BAC, you get the same hash code. Now to do that, if you have a different requirement, such that you want ABC and BAC to have different hash codes, then you go to find some other function that is actually, and one of them is the polynomial function, which in this case, we basically raise any component to some coefficient, in this case 27, to the power, right, of any number of components. So in this case, if the string is of length 3, so then our coefficient is going to go to 2, right? So it's going to be 27 times A, for example, 27 squared times A, 27 times B, plus 27 0 times C. But 27 0 times C to the power 0 is 1, right? So it's as if it's not there. So then in this case, you have a polynomial function that encodes it differently. Now, if you change this to BAC, then your equation is going to be 27 squared B plus 27A plus C. Now, these two quantities are not going to be the same because you are multiplying them against a different coefficient. And therefore, it is going to encode the sequence well. Okay, so this is the idea behind the polynomial function. Now, the last one is what we call cyclic shift. Essentially, what it does is that think of this as doing similar thing, like we are trying to encode a sequence. which means that every time you add something to it and then you shift it, you're doing a transformation. You're transforming one integer to another integer. Just like what we do here is that we are transforming one integer to another one by multiplying it with some constant. But we are not going to do it through the multiplication strategy. We are going to do it through the shifting strategy. So so let's take a particular value of integer. In this case, it's the 2-bit value. And if we do a 5-bit shift, it means that we are going to shift everything to the left by 5. And then we are going to knock off, right, some number of bits that get pushed out of the range. And then we're going to just allow them to cycle over to the end. So which means that for this 32-bit representation, the red one is going to get pushed out, is going to rejoin at the end. So now you get a different value, right? So this 32-bit is going to give you some integer. After shifting, it's going to get you a different integer. It's as if you have done some form of transformation, like multiplication, division, or whatever it is, right? But the end outcome is that you have done this transformation to this particular integer. Now, if you do this repeatedly, like in the way that it's being done here, right? So what it means is that I take a value, let's say a, right? So I'm going to shift a into a prime. So a prime is going to be another integer that starts out from a, but I do a 5-bit shift. Now, after I've got a prime, I'm going to add on to the next character, which is b now, right? So which means that in this case, I'm going to have, at the end of this, my h1 is going to be a prime plus b, right? Okay, so I'm sorry. So let me do over it. I should start from 0, okay? So initially, I start from h. My h is 0, so I can do any kind of shifting. I'm just shifting to 0, so it doesn't change anything. So my first h1 is a, all right? Now my second time I go through this loop, I have h2. Now my h2 is whatever my previous h1 is, which is a. I'm going to shift it, right? So I'm just going to use prime to say that I have shifted it, and then I'm going to take b, right? I'm just going to add it on. Then I get another integer. So then the third round, I'm going to take my h3, which is my h2 shifted. So I'm going to have a prime plus b shifted again, then plus c, right? So the end outcome is that the shifting is going to encode the effect of the sequence, because what you're shifting is a different integer each time, depending on the combination that you have so far. So in that case, you are still encoding the sequence of the elements within it. So that's why the reason why from ABC, BAC, you in the end get different hash codes. You get different hash codes between the two, okay? All right, now maybe just a quick thing for what we are describing here at the top. So how do we accomplish this shift, right? I mean, it's easy to see by hand, right? But programmatically, you would have to do it through the code. And in Java, it's basically done in this way. So you take the same value, you shift it 5 to the left. What you're doing is that you're taking the last 27 bits and then push it to the left. The rest are zeros, right? So think of it like a mask. You're going to mask away the 5 bits at the beginning, remove that, and create some space at the end. Now, the second operation here, shift to the right by 27. So it means that imagine everything get pushed out, and then you have some 27 zeros preceding this now. So then this is what you're going to get, right? Effectively, what you do is that you're keeping only the 5 bits that you have previously at the beginning and push it all the way to the end. So then the last operation, the OR, is just basically stitching them, because the zeros don't have an effect as far as the OR operation is concerned. So you just stitch the two parts together, and then you get a cyclic shift. Okay? All right? Okay. Okay, now we are going to shift our attention to the idea of the collision. And when we talk about collisions, it turns out that we have some coefficients and parameters to all these functions, and we want to choose them in a careful way so as to minimize collision. Now, why is collision bad? Now, that takes us back to this idea, right? So we have buckets. So if they collide, so multiple keys have the same hash code, so they're going to in the end go to the same bucket. So if too many of them go to the same bucket, in the end, when I go to that bucket, I have to be searching for things. And that's going to slow me down. So I don't want a big bucket. So what I want is a lot of small buckets. Because if buckets are small, at most, I just need to do 1 or 2 more comparisons, right? With respect to that. So how do I get small buckets? Well, I get small buckets by minimizing collisions, which is what we have here earlier, that there is this particular experiment with English words. So they just try to compute the hash code to all the English words. And then they try to see, all right, what kind of cyclic shift would give us the minimum collision. So it turns out that 5 give us the minimum collision, like at least we only have 190 collisions out of 230,000 words. That is very little collision for that many words. So in that case, we may decide, all right, I'm going to take 5 to minimize the collision. Now, having said that, right, we can minimize the collision, but we can't drive it down to 0. In fact, there is no way to guarantee that it's 0. Well, there is one way to guarantee that it's 0, and the only way is to create an array big enough to cater to every possible keys, regardless of whether they're going to occur or not. So, but that is exchanging or trading off speed for space, because now you have to allocate such a big array, most of which you may never use, and that itself is a problem, right? So that means that the remainder part, then we're going to talk about how do we handle this collision. Okay, before we do that, right, just take a look at an example. Okay, so in a linked list, right, a linked list contains a set of objects. By the way, this is the actual implementation of the singular linked list that we saw before. Now, singular linked list itself is a set of objects, right? So now let's say what you want to do is that you want to put lists inside hash tables. So you're going to have a hash table of lists, which means that the list itself has to have a hash code. So now you need to implement a hash code for the list, right? Now, in the list, then you have to decide within the list, when I compare 2 lists that has the same set of elements but in different sequences, are they the same list or not? So A followed by B followed by C, and B followed by A followed by C, are they the same lists? Well, that is for you to decide. Depends on what your application requires. If you're using a list structure to store sets, then in the case of the set, they are both the same set. So in that case, you don't want to encode the sequence. But if you decide that these are 2 different lists, then you want to encode the sequence, and this one does encode the sequence. Basically, what we do is that we iterate over every element in the list, and each of the elements, right, we don't know what is that element inside, right? It could be a string, it could be an integer, it could be a float number, it could be double, it could be anything. But what we know is that every object in Java has a hash code. So now we can build our hash code on top of their hash codes. So if a list has 5 strings, each of the string has a hash code, then the hash code for the list is going to be some combination of the hash code of the strings. All right, so you may even have list of lists, I mean, if you want to, right? So in that case, then your hash code for the list of lists is going to be a combination of the hash code of the individual list. So in this case, you can employ the same cyclic shift. Just take the hash code one at a time, and it is always an integer. And then just take a XOR, right? I'm sorry, this is, yeah, you first do an XOR, and then after that you have a cyclic shift. If you don't like the sequence, then you just need to remove the cyclic shift, then you get a set, right? Because the first line is an XOR. The next line is the cyclic shift. Okay, all right. Okay, so now we're going to move away from the hash code itself, which is parked with the object. We're going to talk about the implementation of the hash table. And the implementation of the hash table is going to inherently have a size limitation. because you're not going to have an unlimited size. So you have to fix the size. And let's assume that the size is n, right? Okay, so let's assume that the size is n. All right. Then we know that the array can only go from 0 to n minus 1, right? Because if the array size is n, then that is my address space, 0 to n minus 1. So then how do we then map such a big range like the integer range? And the integer range is minus 2 to the 31 all the way to 2 to the 31 minus 1. How do we go in that way, right? Well, in this case, we have to squeeze it down to the range of n. And one of the simplest way to do that is just to take the modulo n. Okay. Now, the effect of doing the modulo n is that now we have created a second reason for collision. Now, the first reason is when you have two keys mapping to the same hash code, because the hash code itself may not have been well designed. Now, the second reason for collision is when you have two different hash codes mapping to the same index in the array because of the limitation of space within this array. So in this case, you might still have two different hash codes that get mapped to the same index. And that is another layer of collision. So that means when you eventually get collisions in the hash table, it's a factor of these two. It is a factor of how well designed your hash code is. It is a factor of how big your underlying array in the hash table is. Now, and in practice, what we have found is that n that is prime is better. N that is prime is better. Okay, so let's take a look at this example, right? So you have the following hash codes from some data distribution. So let's say 5, 10, 15, and so on, right? If you use some non-prime number, then it's going to accentuate the kind of patterns that you might see. So which means in this case, mod 10, then because these are divisible by the same number, which is 5, right? So in that case, then any multiple of 5 is going to result in a lot of collisions. So, well, in this case, right, for example, all of them is either going to go to 5 or 0. But if you do a slight change, just change it to 11, which is a prime number, then it's going to be more or less well distributed, that you don't actually get collision. So you tend to choose an n prime. It doesn't mean that doing that you will remove the problem completely, because you can still have a problem where there is a pattern that is a multiple size of your prime. That means your prime is n, but you are basically getting a multiple of prime, and then the remainder of Pn plus Q is always going to be Q, right? Because if you take this whole thing and mod n, so then the first part is going to basically leave a remainder of 0. Then the last part is going to be Q, so it's going to be Q. So if you want to deal with that, right, then there is a more complicated function. Call it multiply, add, divide. Basically, the idea is that instead of one prime number, you take two prime numbers. The actual size n and something that is bigger. Let's call it p, right? P is a bigger prime number. And then we are going to augment the original hash code by two things, right? We multiplied by a, we added by b, and then essentially we divide it by p, right? And in that case, a and b are going to be chosen randomly from this, right? Now, if we compare this, well, I mean, the array is too small, right? I tried this on these two particular combination of them for specific a and b and p. They are more or less comparable, right? In this case, mainly because the data set is relatively small. But if your data set is very big and you start to see some of these repetitions, then a more sophisticated compression function might help you. But I mean, yeah, so that's the thing, right? Okay, so let's then talk about how do we implement a hash map, right? And there are some key concepts that we want to see. All right, so let's take a look at this. So you have a hash value, right? And this hash value is, what do? Is that you get a hash code. So remember, where do you find this hash code? You find it inside the object key. So that object is the one that has to decide how to implement the hash code. Now, but once we have that hash code, which can range in the integer range of -2 to the 1 to 2 to the 1 minus 1, we need to squeeze it down to the capacity. And if we have this capacity, then we need to have a compression function. So now this is now compression function that basically based on the MAD what we talked about earlier. So you multiply it by some scale, you add some shift, you divide by some prime, and then you finally divide it by some capacity. Now, the capacity here is the size of your current hash table. And okay, there is something about load factor here. We're going to talk about this a little bit later, right? But the idea here is that if you have too many items, then you may want to resize. So resizing means that you're going to create an underlying array that is going to be, well, in this case, twice as big, right? 2 times minus 1. Okay, why 2 times minus 1? Well, you kind of want to make it more likely to be prime. So instead of 2 times that value, which will make it non-prime, you take 2 times a prime number minus 1. Maybe that's more likely to be prime. Okay. All right. So now, when you resize, you have to rehash. Okay. So because when you resize, all the relationship between the hash code and the hash value is going to change because it's based on a specific capacity. Now, but we don't need the hash code implementation to be changed because it's within the object. All we need to do is that because we have change capacity, so we have to recompute all the hash value with respect to everything that is currently in the hash table. So think of it like, we talked about this a long time ago in the notion of amortization, right? So you double up the array and then you go through shift everything down, right? So basically you have the same problem here. So, and on the other hand, you can amortize that cost. Although every time you double up the size of the hash table, you incur more or less an O(n) complexity, but you don't do this often. So then over the long run, you can average it out. So then you can maintain more or less almost similar type of complexity as the individual operation itself. Okay. All right. So now, having said that, there are collisions. So we still need to deal with it. So then we're going to talk about a couple of ways to deal with collisions. Okay. Now, the first way to deal with collision is what we said before, which is the notion of buckets. We call it separate chaining because effectively you can imagine this to be some form of list, right? You can even imagine this to be some form of linked list. But the idea is that this is going to be something that can grow over time, right? That you don't need to specify beforehand what is going to be the size. So that means that you don't commit necessarily to what is going to be the size of the secondary storage, right? But you have to commit to this one. And this one is the capacity. So you have to commit to this beforehand because you instantiated with this and you're stuck with that. And whereas the list, the size of the buckets can grow and shrink depending on the actual number of stuff that go inside there. Now, in the case of the separate chaining, every time you have a collision, just pile it up in the bucket. So 54 comes, 52 goes in, right? 28 comes to the same one, then it just goes in. 41 comes, it just goes in. Now, which means that we have to be searching through this bucket every time we need to do something. Suppose that you need to do a get. You're looking for something, right? 41, for example. So you compute your hash function, and based on the hash function here, right, is an O(1) operation, right? Computing a hash function is more or less O(1). So because you just have a one line, and everything is a mathematical operation. Then you come here, and then you find a bucket. So then you need to be searching through the bucket to see where is 41. Now, if you use a simple implementation within that, let's say like the list or something, right? Then you're going to be doing linear search. And this linear search, in the worst case, is going to be O(n), right? O(n) is going to be the number of items inside that bucket. In the worst case, everything that you have comes down in a single bucket. So in that case, then it's going to be O(n) with respect to everything that is inside the hash table. So which means that the worst case is still On. Okay. Now we start talking then about what we call the load ratio. So the load ratio is the number of elements to the size of the capacity. So the capacity here is N, big N. The number of elements here is the summation of all this, right? So that is your small n. So then we're going to take the ratio of small n to big N, and we call that the load ratio. The larger it is, the more worrying it is. Because the larger the load ratio, it means that you have a lot of stuff. You don't have a lot of space. So in that case, then you are much more likely to have collision. So you get bigger buckets, and bigger buckets means you need to spend more time searching. And that is the problem. So when your load ratio increases, right, it's time to get a little bit worried. Now, on the other hand, if your load ratio is low, then you're going to be faster, right? Because your load ratio gives you an expectation of what is the average size of the bucket. So if the total number of elements is n, and the total number of buckets is big N, then on average, each bucket is going to have that many elements, right? So if your n is big, right, as your big N is large, which means that you create a lot of capacity, so this load ratio is going to be low, and then you're going to approach O1 time complexity. Now, then what happens when your load ratio is going to be big? Then it's going to approach On. So then what do you do? Well, then we can go back to this one and realize that once the capacity, right? So if the N is bigger than capacity divided by 2, right, which means that the load factor now is greater than 0.5, we're going to resize it. So which means that we are going to sacrifice about half the space in order for us to maintain quick enough retrieval operations that we do that. So this is a direct trade-off between speed and space. Now, what if you need to put, right? Now, putting something, in theory, to put something to the bucket, just expand the bucket. That is O1, right? Well, then it will be O1 if you don't need to worry whether the element is already in there. But because we have the constraint of uniqueness of the keys, before I put something new in, I have to check whether or not it already exists. And checking whether something already exists is the same as getting. So in that case, then I'm still going to be On in terms of the putting, right? Now, this implementation is called the chain hash map. This is like separate chain, right? So if you see here, right, to get the bucket, right? So the bucket here is implemented as an unsorted table map. This is our first thing that we talk about in this slide. And because it's an unsorted table map, when you get this, is going to do linear search inside. Now, to put it in, we still need to do a linear search inside, right? Because remember that within the put, we still have to find that it's actually unique. Okay. All right, so this is going to be the last big concept for the hashing. Now, the issue with the previous one is that we are shifting the burden of storage from the main array to the secondary storage. Secondary storage here are the buckets, which means that all the spaces are still going to be empty, right? So that means that it's not going to be the most efficient implementation that we have. Because if most of the spaces are empty, in fact, instead of occupying the spaces that we have already allocated, we are now creating new spaces that we have not allocated. In effect, what we do is just wasting space, right? In some sense, that's what we do. Because remember, an array, you allocate the space beforehand. So all these things are already pre-committed. The buckets are not yet. You only commit it when you need to. So having committed all these empty spaces in the array, I still have to waste them because I'm not going to fill them up. So based on that idea, then a different type of collision handling is what we call linear probing. And the idea of linear probing is that let's not have a secondary storage, because that misleads us in terms of the usage of the space. So why not we just reuse the empty spaces in the main table itself? Now, which means that if I'm going to hash something, let's say 15, inside here, well, the cell may already be occupied. Then I just need to go on and find the next empty space. And where is the next empty space? Neighbors, right? So since the index 4 is not available, so then we go to 5. 5 is not available, we go to 6. 6 not available, we go to 7. 7 not available, we go to 8. And finally, there is an empty space, so you put 15 there. Right? So that is, now in this case, effectively you still have the buckets. But the buckets is in the array itself. So you just have to find the neighbors, right? So we are making use of the surrounding spaces to keep track of all these additional things, right? That basically happen because of the collision. Now, in the case that you don't expect a lot of collisions, this doesn't happen often. And that's what you hope, right? If you have chosen your hash code well. But you can't guarantee that, right? Because sometimes it could happen. Now, let's say, right, in this particular case, right, you get a better way of using the spaces inside. In fact, when we compute the load ratio, it is now a better estimation of the actual space that you're using, because there is no more secondary spaces. So which means that you have allocated a size of an array, and then you just need to know how many are you using. In fact, you have used all of them, right? Because that's how much you commit to. But we know how much empty spaces we have. So in that case, then we can be efficient in terms of space. Now, but it does create another problem in terms of the way that we have to keep track of insertion and deletion. Now, so let's say, okay, I'm just going to use another example, right? Let's say I'm going to do 17 now. And let's say, just for the sake of argument, right, that 17 is going to hash to 4 as well, right? So then I'm going to go in the same way. So I'm going to go 4, 5, 6, 7, 8, still full, but now I can put 17 here, right? And then I decide that I don't need 15 anymore. So I can remove 15, right? All right, so then I want to check for 17 again. Now, when I check for 17 again, so I'll go through the same route, and then I find an empty space. Now, what does that mean? It means it's an empty space, and I didn't find 17 yet. So I would conclude that 17 never happened. And therefore, I'm going to return and say there's no 17 here. But 17 is actually there, right? And what happens here is that we are getting misled, because there used to be something there that is no longer there. And 17 was inserted at a point of time when something was there, and therefore we skip it. When something was removed now, we think it's an empty space. And that's, but in fact, 17 actually is later down the line. So which means that in this case, you don't just have 2 states to each array space, you have 3 states. So you have the state of being filled, you have the state of being empty, and we're going to have another state that we call defunct, which means that this is the state of currently being empty, but previously occupied. And we need to understand this part, because if we are looking for 17 and we say that this is a defunct cell, which means that there was something before, which means that when you're searching for something, you shouldn't stop here. Keep going. You keep going, because what you're looking for might be down the line, because maybe you inserted this thing beforehand when we still had something in that cell. So then means that now you have to care about these 3 states. Okay, so but that gives us information, because if it is empty, we can stop. Because empty means that it was never used. It means that nobody ever goes past that empty cell whenever they do linear probing, right? They search for an empty space. The first time they encounter an empty space, they're going to stop there. So which means that if I'm looking for something and I encounter upon an empty space, I don't need to keep going. Because if what I'm looking for was there, it would have filled that empty space. So in that case, then for empty space, I can stop. But if it is defunct, I cannot stop. I have to keep going. All right. So that's the key idea behind the linear probing. Now let's take a look at how that is implemented. Yeah. When you hit an empty spot. But 7. Oh, well, you stop either you meet an empty space or there is no empty space. So then you have cycled over to the original one. So basically you do a circular search, right? Yeah, but in this case you wouldn't, right? Because there are still empty spaces. So there, you will stop at some point. Okay, so let's say here is the implementation of the probe hash, which means it's a hash map that is based on linear probing. Now in this case, we want to find a slot for a hash code H and the key is K, right? Because we have to check whether or not the key is there. So we're going to start looking at where the hash code is, or the hash value instead. So J is initially H, right? H is the hash value, so I'm expecting it there. So in the case here, let's go back to the example of 15, right? So in that case, then the initial H value is going to be 4, right? So 4 becomes into. So we start there, and then we come inside here, and then we ask, well, is J available? Now, the same function is going to be reused in 2 conditions. One is when we are trying to get something. So that means we want to know whether the key is there. The other one is when we are trying to put something, and we are trying to check. Well, we are trying to check 2 things when you're trying to put something. Is the same thing inside for check of uniqueness, right? And the second thing is that if it is not inside, where should I put it? So I should put it in the first available space, right? So which means that here I'm going to start from the original location, which is pointed to me by the hash value. So I'm going to ask, is that space available? All right, so if it is available, there are still 2 possibilities. Is it empty or is it defunct, right? Now, if it is available, right, well, then I'm going to record the first available spot. I need to know this because I'm going to put something there, right? If I'm going to put something there, I need to know where is the first available spot. And then I'm going to check, is it null or not? Well, if it is null, it means it's empty. If it is not null, it's defunct, right? So if it is null, it means that it's empty. I can stop. Then I just need to get out, right? So which means that I have found an available space and I can have stopped searching, right? Now, if it is not null, then it's defunct. If it is defunct, then I cannot stop. So then I'm going to keep going. So I'm going to keep going to the next one. Well, if it is not available, it means it's occupied by some key. Now, is it occupied by the key that I'm looking for? If the answer is yes, I can also stop because it means that I have found what I'm looking for, right? If I don't find what I'm looking for, then I have to continue. Then in that case, I have a J equals to J plus 1. Mod capacity means I'm doing a cyclical search. I'm just going to keep going until I will come back to my original position, which is H. So which means that in this search, I would have to keep going until I find 3 cases, right? So one is that I find an empty slot, I stop. I find a key that I'm looking for, I stop. Or I don't find the key that I'm looking for. And how do I know? I have searched everywhere cyclically, and I still don't find it, right? And in the end, we are going to return this in terms of this one, right? So we're going to return 2 bits of information, two types of information. The first information is, did I find it or not? And that is given by the sign. So if the sign is negative, it means I didn't find. If the sign is positive, it means I found it. Now, the second piece of information, well, if you find it, at which position? If you didn't find it, what was the first available position that I can put it in? And that is going to be given to you by the index, which is the this is going to be the index. All right, so you return 2 bits of information, whether I found it or not, and if I found it, where it is. If I didn't find it, where is the first empty slot that I can put it in? Okay, so that is the find slot function, and basically you use it every time. Now the only thing is that I would like to point out to you that this is what you do when you defunct. So defunct itself is a node. So that means you create a special node called defunct. And if you remove something from a particular cell, you don't leave it null. Instead, you put in like basically it's a sentinel. It's another sentinel that codes for a specific value, which in this case, the specific information that something was there and has now been removed. Okay. Now, the issue with the linear probing is that you get bunching. So bunching is what happens when you have certain parts and they're all occupied, and then you leave a lot of empty space, and then you get another cluster of stuff, right? And the reason is because all the searches we do is all nearby. So which means that we're going to fill up the nearby space, and technically we are now making it less and less random. Within the cells are no longer random. They tend to happen in a particular clustering fashion. So if you want to break out of the randomness, then we can try different schemes. And these are 3 different schemes that we can use to break out of this bunching property. The first one is called quadratic probing, right? Now the linear probing means that you try +1, +2, +3, right? So you go in the neighborhood. In the quadratic probing, what you do is that instead of +1, you +1 squared, +2 squared, +3 squared, right? Now the effect of this is that 1 squared is 1, 2 squared is 4, 3 squared is 9. So which means that if you try once, let's go somewhere nearby. Oh, I can't find a space. Let's go to a further neighborhood. I still can't find a space. Let's go further. And the idea is that you're going to move away from where the bunching is happening. So if there is a bunching here and you try this one, no, cannot, right? Then you take a bigger step. And I said there is still something here. Then you take a bigger step. So the steps you take getting bigger and bigger, right? But at some point you have to stop, right? And you stop after you try all the possible I from 1 to n-1. Now the second way of doing this in a random way, well, pseudo-random way. So you have this pseudo-random generator that is going to give you a predictable sequence of random numbers. Okay, I mean they are random numbers, but you want to make it a predictable sequence. So usually they are controlled by some kind of seed value. Same seed value will give you the same sequence of random numbers. So which means that you just need to maintain the seed, right? And then it's going to generate each time a random number. So for example, the first one you plus 21, for example, and 21 is not, right? Plus 19. And then it fails, then you take a different one. Okay, let me try plus 7. Okay, it fails, let me try plus 73, for example. So then you get this sequence of random numbers to try to search for it. The last one is what we call the double hashing. Now, double hashing means that, well, all this probing is independent of the key, right? They're only independent of the sequence, right? Whether it's 1, 2, 3, 1, 4, 9, or something. So why don't we probe in a way that is sensitive to the key itself? So which means that we're going to hash a second time. Now, the second hash is not going to be an independent hash. The second hash is going to add to the first one, right? So which means that we are going to still have the I, which is a sequence here. And then we're going to use a second hash function, h prime, to rehash it. So which means that the jump that we have is now going to be different for every key. So the quadratic is going to take the same jump for different keys. So still 149, right? The pseudo-random still take the same jump for every key. So double hashing is going to take different jumps for different keys. So that is the benefit that you get from that. Okay. Now, if you do all these things, right? What do you mean, use cases? Depends on your data. So I think the idea here is that we can't tell, right? So in what pattern your data actually comes. So if your data comes in a particular fashion where, for example, names of people. So names of people are not really random, right? So you have different spellings of the same name, right? So there'll be some similarities, right? So which means that the hash code is still based on the key, which means that it's still sensitive to some extent to the content of that. So in the way that if your data comes in a non-random way, you might end up with a non-random distribution, which means that you have more collisions. So now, if you can always forget about these things, and then you let the collision takes its place. Now, but if you really want to optimize for it, then you would do some experiments with the actual data distribution that you have to actually test what sort of mechanism is going to allow you to distribute your data as evenly as possible in your hash table, because then that's really going to optimize the performance of your put and get. Okay. All right, so in this case, the hash table, well, the expectation is O1, right? And most cases, you should be able to do O1. If you can't get O1, just increase the capacity. And at some point, you're going to get O1. But of course, that is you're paying for that with the space capacity. Now, in the worst case, it's going to be ON. Most likely, you can avoid this case. Most likely, right? In fact, sometimes if you really use a hash table, and then you start to realize, hey, why is it slow? It's not as fast as you're expecting. This is one of the cases that you need to figure out. That means like, okay, is there a lot of collision? What can I do with it? And how do I break apart that collision into different parts of the array? So in that case, although the worst case is ON, there is angle that you hold, which is the space capacity, that allows you to do this in O1 time. Okay, on average, right? Okay, now just to get a little bit of practice and just to clarify the concept a little bit, right? Let's do this for the next 10 minutes or so, right? And then we can discuss it. Yeah, I would still like to be able to go to the first part of the next topic, just the easier part, right? We're not gonna get more. Okay, let's try it out. The next 10 minutes or so, right? Figure out how you can do this handling by chaining. If you do it fast, then you can even try the probing. Then see how your numbers are gonna get distributed across the array. We have a number of keys, and then we are given a hash function. The hash function is 3k plus 5 mod 11. So the 3k plus 5 comes from our hash code. The 11 comes from our compression function. That's the capacity of that, right? All right, so let's say we take this key and we're going to insert them one by one. The sequence of insertion is going to be important, because when we resolve the collisions, who comes first is going to have an effect as to the final way in which they are stored. So in this case, let's say we say it's an 11 entry hash table. So in this table, we have 0 to 10, right? So, all right, so we're gonna compute. So this is the key, right? And we're gonna compute the hash of the key, right? And let's say this is, well, it was just now, it was 3 times this plus 5, right? I think that's correct, right? Yeah, 3k plus 5, but we want to compress it to 11. So I'm gonna put in a mod function. And that's it, right? And then I just need to copy it over to the rest. Then I'm gonna get, well, these are the expected indices. Okay, so then we start, right? And we are going to call this separate chaining, okay? Okay, so, well, the first one, 12. 12 is expected to go to 8. So 8 was initially empty. So now we create a bucket, and the bucket is gonna contain 12. Then we have 44. 44 is supposed to go to 5. So then we put 44 here in its bucket. 13 is going to go to 0. So we expect 13 here. 88 goes to 5. 5 is already occupied. So we are going to put it into the same bucket, but it's going to go after 44, right? And then 23 is again index 8, already occupied. So then we put it here. And then 94 is supposed to go to 1. And then 11 again goes to 5, right? And 39 goes to 1, it's already occupied. So we just join the bucket. So 20 is going to go to 10, right? And 16 is going to go to 9. And the final one is 5. 5 goes to 9. So then in that case, we are going to join that bucket. So in the separate chaining, you should have something similar to this, right? So each of this is a bucket. In the particular case, is basically an array list that contains these elements. All right. And so now, if you had started with a different size hash tables, then you're going to get a different thing, right? But size 11, you should get this one. Now, let's try to do this, but we're now going to do it for linear probing, right? Just to get clarity in terms of this, right? And, okay, same index. So we're going to put it here. And, okay, 12 comes, it goes to 8. All right, so 12 is going to go there. 44 goes to 5. 13 goes to 0. So far, no problem, right? So 88 goes to 5. Now, 5 is already occupied. So if it is linear probing, then we're going to go next door. So in that case, we're going to go to 6, right? And then 23 goes to 8, but 8 is already occupied, so we go next door. 94 goes to 1. 11 goes to 5, it's already occupied, next door occupied, so finally we find 11 here. And 39 goes to 1, but 1 is occupied, so we go next door, right? And then 20 goes to 10. And 16 goes to 9, 9 is already occupied, so then we keep going and we find the first location here, right? And the final one is 5, right? 5 starts at 9. And we have to cycle through until here before you find a spot, right? Now, in this case, everything is stored in the main table itself, and we haven't assumed that we have resizing, all right? So we haven't talked about resizing yet. Well, the resizing depends on the load ratio, as what we saw before. Technically, you're going to resize when your load ratio goes above a certain amount, but here we're not assuming there is any resizing. Now, what is interesting here is that technically the buckets are still there. So here you have a bucket, 44, 88, 11, but your bucket is vertical. Here you still have a bucket, but your bucket is horizontal. And worse than that, well, in case that your bucket sometimes actually contains other people's buckets. For example, right? You start at 16, right? Or 5, right? Well, it's supposed to go to 9, right? Then you have 23 and 20. And 0 and 94 and 39 and 16, right? This is effectively now all your bucket. Because whenever you do searching, you have to cover all these things up to here, right? Now, whereas in this case, your bucket only has 2 elements, but here your bucket is bigger. Because then you just keep going horizontally until you find that particular element. So that is the trade-off that we are doing. Well, on the one hand, this is more space efficient, because we are not wasting all the spaces that is empty. But at the same time, in some cases, we might also cause other problems, because the other problems may come in due to the resolution of the collisions, which in the case of linear probing, because we overlap in terms of all the buckets, in the end, some buckets may actually get merged together. So that feeds into the previous concept as to why is it that you want to avoid the clustering or the bunching, because a cluster essentially is like a bucket. Because when you search for something there, the chances are you need to go to the nearby elements. So if you have areas where there is a big cluster, it means that you have ended up with a situation where you have a big bucket. The situation that you want is that you want a lot of empty spaces in between, which means that on average, your bucket size is small. And if your bucket size is small, most of the time you just need to search a few neighboring region until you meet an empty space, and then you can stop. So just like in the separate chaining, you only need to search within your bucket. In the linear probing, you need to keep searching until you meet an empty space. So those are how the two concepts are kind of related to one another. Okay. Okay. At this point of time, any questions?